J174 crosses. So in the GitHub link below, you can find the problem statement. And in that page, you can also at the bottom find a link to the original version of the problem at the HKOI online judge. But you don't need an account to see the problem. I've already summarized the entire problem in the GitHub link below. So the problem is about crosses. Crosses on a Cartesian grid that's n by m in size. N and m will be specified by the problem input. The input also gives you k points, each with x and y coordinate on this two-dimensional grid. And our job in this problem is to count how many crosses would contain all of those k points. So what is a cross here? So you can see this is a cross. This cross has 5 points along its two diagonal axes. This is also a cross. This would have 4 points along its two diagonals. And as always, the best way to understand a problem is to look at its sample input and sample outputs. And these are the original sample inputs of the problem. The first case is 22102. So we're looking at a 2 by 2 grid, as you can see on the screen here. K is 1 here, and so there's only one red dot. So go ahead and hit pause and count how many crosses contain this red dot. Alright, did you get it right? This cross, yes, and this cross both contains the red dot, so 2 in total, and that's the answer. Now let's look at input sample 2. 2 by 3 Cartesian grid, and there are 2 red dots, k equals to 2. And so let's count how many crosses contain those 2 red dots. This cross? No, because it only contains 1 red dot, not 2. But this cross contains both red dots. And it turns out that that's it. The answer is 1. There's only one cross that contains both red dots in this grid. From now on, we're going to draw squares instead of crosses. Squares are a lot easier for me to draw. But squares, crosses, they're the same thing. Just two sides of the same coin. And it turns out in this problem, the best way to tackle it is to start with subtask 5, where k equals to 0, because this case would lend us very important insight that we will need down the line. Can't do anything without this insight. So what is the problem when k is 0? It means there is no point. That means we need to count all the possible crosses or squares in this Cartesian grid. So this grid is 5 by 4. So go ahead and hit pause and try your best to count all the crosses on this grid. Let's see if you get it right. Well, if you count all the squares of size 1, there are 5 times 4 squares, 20 of them. What about size 2? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you see on the horizontal axis, you have 1 fewer choices, so 4 instead of 5. Along the vertical axis, you also have 1 fewer choices, so 3 instead of 4. So now it's 4 times 3 instead of 5 times 4. What about size 3? 1, 2, 3, 4, 5, 6. So 6 squares of size 3. And size 4? 1, 2. So a total of 40 squares in this scenario. Alright, but what about a general solution for subtask 5 for any n and m values? Can you see the pattern? Well, let's see. When size is 1, there are n times m squares. When size is 2, there are one fewer choices along both the horizontal and vertical axes. So n times 1, n minus 1 times m minus 1. When size is 3, there are 2 fewer choices along both axes, n minus 2 times m minus 2. And you keep increasing the size until the size is m, and assuming m is less than or equals to n, that'll be all, because you don't need to worry about any squares of size larger than m. You see, then you can write some very simple loop to add up all these numbers. And that's the pseudocode. Very simple, right? Subtask 5 is actually very simple if you can see the matrix. Now, what about cases where m is larger than n? Well, here I just iterate I from 0 to the min of n and m to take care of that scenario. Moving on to subtask 6, k equals to 1. Well, now you're actually ready to implement a brute force solution because you now know how to iterate through all the possible squares. But let's hold off for now. If we solve subtask 6, we're going to gain some more intuition that will be useful later. So k equals 1 means there's only one red dot. And let's consider a 7 by 6 grid and one red dot in the middle, 4, 2. Now go ahead and pause it and try to count how many crosses contain this red dot. Okay, so 4 here. And you see, as we move the lower left corner of the squares that we're drawing up and to the right, we're still getting 4 squares. We can draw 4 squares here, but as we move it up and to the right, this time there are 1 fewer squares that we can draw. So 3 only here. And if we keep moving this lower left corner up and to the right again, we'll realize that there are no more squares that can contain this red dot. And so we're done with this diagonal. And now we're going to move on to the other diagonal. Alright, there are 3 squares here we can draw. And notice how this time we're anchored around the top left corner. And if we move the top left corner down and to the right, 3 more squares, and 3 more here, 3 more here, but finally only 2 at the final step. So the total is 25. That's the answer, right? Not quite. You see, there are these squares. Can't you see that we are double counting? These 2 squares have center exactly at 4, 2 at the red dot. And whether we're going through one diagonal or the other diagonal, those 2 squares will be counted. And so to get the correct answer, we have to subtract out the double counted squares, which makes 25, 23. 23 is the answer. So what about the general solution? Let's start from scratch again. So in this case, we can draw 4 squares, right? Let's look at the horizontal direction. We go from the vertical line from the red dot, and we can draw 4 vertical lines to the right. And then we look at the horizontal line. So in that case, this is n minus x naught plus 1. Now, if we take the horizontal lines that we can draw from the red dot and move up, we can draw 5 lines, which in this case is m minus y naught plus 1. And the number of squares we can draw is the lesser of those 2, which is the min of n minus x naught and m minus y naught plus 1. And in this case, we can do it twice and the answer is still the same. But the third time, the final time, we can draw 1 fewer squares than before, than we normally can. So can you see how many 4s there are? Well, the general formula turns out to be the min of x naught and y naught. So that's the formula for this diagonal. Now let's try the other diagonal. You see there are 3 squares you can draw here. And the general formula is also, you consider drawing the horizontal lines and then draw more horizontal lines down below. You can draw y naught plus 1 horizontal lines. And toward the right, if you draw the vertical lines and you move to the right, you can draw n minus x naught plus 1. But it's the lesser of the two that tells us how many squares we can draw. And so that's the formula. And we can draw that many squares many times. How many times? Well, it turns out to be the smaller of x naught and m minus y naught. And again, the final time, we draw one fewer squares than we normally could. And so the formula is this for this diagonal. Okay, but don't forget to subtract out the double counted squares. And that's the entire formula for k equals 1. This will solve subtask 6. And take a minute to make sure you fully understand this formula, because all these intuition will really help you when you try to understand the full problem. Okay, now let's try to implement a brute force method. We're going to implement an algorithm that will solve the problem correctly. It's a very important first step. Even though it's a brute force method, therefore it's very slow and it won't score us many points. But if we don't have a solution that is correct, it'll be very hard to move to the next part to solve the full problem. Because as you optimize your algorithm becomes more complex, which means that you're likely to make mistakes. You're likely to have errors in your input-output. And if you don't have a correct solution to compare and benchmark against, it'll be very hard to find the bugs and to diagnose the problems in your optimized but complex solutions. So brute force method is usually a very good way to start solving the problem. And so let's begin. To help us visualize, let's have a concrete example to consider. And we're going to choose a 5 by 4 Cartesian grid here. N is 5, M is 4. We're still going to assume n is larger than or equals to m from now on. It's really a harmless simplification here. And notice that subtask 1 and 4 involves n and m always less than or equals to 3000. So let's focus on that for now. You'll see why it's a great, useful simplification later. So now we're ready to implement the brute force method. And as you might be able to see, the simplest way to solve this problem is to go through every single possible squares and then examine the two diagonals and check how many points are on that diagonal. And if the number of points turns out to be k, then that particular square should be counted. And if we keep track of it, eventually the ultimate count is the answer. So the pseudocode is this. It's conceptually very simple. S, you're looping S from 1 to m, that's the size of your squares, and then you go through every single point on the n by m grid as the lower left corner, and then you examine the diagonals and count the points until you find one that covers all k points, and then you add 1 to crosses and then print crosses. The tricky part is, what's the best data structure to store those k points, the xy, efficiently so that you can retrieve them later? Remember, you have to check how many points are on the diagonals, right? So either you go through all k points and then see how many of them are on the diagonals with the center that you're contemplating, or you go through the diagonals and then see how many are one of the k points. So other than that, you also have to deal with the problem when n is less than m, but I'll leave that up to you. It's a simple problem, so I'm sure you can solve that, right? So about the first problem, it turns out the best way is to store the k points in a map, a two-dimensional n by m grid. So you initialize the whole grid to false, and then you go through all k points in the input and mark those points on the grid true. And so when you go through all the possible squares, what you do here is you examine the diagonals, and then you count. You just look up the particular grid points and see if it's true. If it's true, then you add 1 to the number of points. And then for all the squares that has k points lying on its diagonals, you add 1 to the count. So what's the time complexity of this pseudocode? Well, you see there's a 3-layer nested for loop on top. So that's easily n times m complexity. And then to examine the diagonals happens to be order of m. So the whole complexity is order of n times m times m times m, which is order of nm cubed. Well, that means this brute force solution can only score the subtask 1. But that's a good start, right? You have now a correct solution. But how do we optimize it? Well, let's go back to the case when k equals to 1 and see what insight we can draw from there. So remember, in the brute force method, you're going through all the possible squares, and that's order of n m squared squares, or crosses, order of n times m squared crosses. But if you take any one of the k points, any one of the k points would greatly shrink the number of squares that we need to consider. In fact, well, let's look at what that means. For example, this red dot on this 5x4 grid and this yellow square cannot possibly include a red dot. It's so far away, right? And you can see there are many squares on this grid that cannot possibly include a red dot. Now the real question is, how many squares on this grid are relevant? Now go ahead and hit pause and see if you can figure out how many squares are relevant here. Well, there are these two. They center at the red dot, and of course those squares are relevant. But there are also these two, and also these two. So those 6 squares are also relevant because the red dot also lie on their diagonals. Now let's look at the other diagonals. You see the symmetry here? Now those six are also relevant. So that's a total of 14 relevant squares. It turns out that if you take that into account, order of m squared squares need to be considered. Well, only order of m squared crosses need to be considered, instead of order of n times m squared. But what's the pattern? How do we enumerate all the squares efficiently in a simple algorithm? It turns out it's the diagonals. Now this square is relevant. This square is also relevant. And this square too. And this also. Now can you see that for a square to be relevant, its center must be diagonal to the red dot? So to take advantage of this observation, you pick any one of the k points. In this case, I would pick the last point, x0, y0. And then you go through every point on the grid that's diagonal to x0, y0. And then you try all the possible radius. Now radius usually refer to circles, but in this case radius is just the distance from a square's borders to its center. So this perspective, this way of framing squares would simplify our algorithm for us. So for now, x, y, r would specify a particular square with the center at xy and radius at r. So you go through every single possible squares or cross, and then you count the number of points that's contained in the square's diagonals. And then you check whether it's k, and then if it is k, then you add 1 to the count. And this is an order of m cubed time complexity algorithm. Better. But remember, Sometimes the centers are not whole numbers. They can be right in the middle of the grid. They can be 1.5, 2.5, 0.5. So when you enumerate all the possible centers that is diagonal to the red dot, bear that in mind. And that's the implementation, my favorite implementation of this algorithm. So you enumerate, you go through every single point on the n by m grid, but make sure that you include all the half point. So x loop from 0, 0.5, 1, 1.5 until n. And so for the y, you also loop from 0, 0.5, 1, 1.5 until m. So you loop through all the points, and then if any particular xy is diagonal to x naught, y naught, then that is a relevant center. And with the center, now you try all the possible radius, and that gives you all the possible squares. But you have to make sure that the radius is not so large that the square is out of bound, right? So XYR would specify a square. You try all the possible combination, and then you count the diagonals and see how many points lie on the diagonals, and the rest is the same. And what's the complexity of this? It's m cubed, right? We know that. But now let's look at this part. Let's hit pause and look at this part of the code and see if you can spot some optimization opportunity here. We can do better than order of m cubed. So can you see the redundancy? You can use partial sum to turn that order of m cubed solution into order of m squared. And this will score all of the subtasks except for subtask 7. That means you're going to score 78 points in the hardest ever problem in the junior final event of HKOI. So in case it's not clear to you what I mean by using partial sum, let's look at this visualization of the idea. We're considering a 9 by 8 grid, and k is 6, so 6 red dots here. The observation is that, well, let's formulate something. A function called count with parameter xyr. It's defined as the number of red dots along the diagonals that's defined by the square with center xy and radius r. Now if you expand the size of the square, make it 1 bigger in radius, then count xy but r plus 1 would be equals to the count of xyr, the count of the inner square, plus how many red dots are on the 4 corners of the outer larger square with radius r plus 1. The center is still xy. So to better visualize what that means, consider xy being 4.5, i.e. the yellow cross here. And if you consider square of radius 0.5, the smallest square here, there's only 1 red dots along the diagonals of this square, right? Okay. Now if you consider a bigger square with a radius larger by 1, so count of xy but 1.5, it would be the previous answer, 1, plus 3 red dots on the border of this larger yellow square. So 4 red dots here. And if you look at a bigger square again, radius being 2.5, it's the previous answer, 4, plus the 2 red dots on the 4 corners of the larger yellow square at the edge. And in fact, if you look at an even larger square, it's the previous answer, 6. But because all 6 points, all 6 red dots have been included in the 2.5 radius square, that means all k points are here. So we would have already counted the previous square as a relevant square. And so any square that's larger than that one with the center xy would be also relevant. Now that's a very important observation that will be useful later on as you optimize further. But for now, you don't even need that to score subtask 1 to 6. So use partial sum and optimize the pseudocode that you had before, and then score all 78 points. And next time, in the next class, we're going to look at how to build the full solution to this